Hi, folks. Welcome back. This is section 2.2, matrix multiplication and linear combinations. Let's go ahead and get started. We're going to define the product of two matrices here. We're going to say that A is an m by n matrix and B is an n by k matrix. For reasons that will make sense in a moment, we require that the number of columns in M and the number of rows in columns in A and rows in B have to be the same. So the number of columns in A equals the number of rows in B. And we're going to define the product AB of these matrices to be the matrix that makes this equation work out, but I want to explain where this equation comes from. B is a matrix, which means that if I have a set of weights, or say a vector of weights instead of a set, then this is a linear combination. And when you evaluate a linear combination, then you get a new vector. This is also a vector. So what if we use this vector as a set of new weights in this linear combination, where this is my matrix and these are my new weights? Then this is also a linear combination. That is, this is a linear combination of a linear combination, where the first linear combination results in a new set of weights that then we use in the second linear combination. What we want to do is compute the matrix that works with the original weights. So what matrix works with the original weights so that we can have a single linear combination that does what these two linear combinations do. So we're combining two linear transformations into one. And so when we figure that out, we're going to say that's the product AB, so that AB, that combined matrix times X, is equal to first taking BX and then taking A of that. That's what we want. So that we can move the parentheses around the way that we're used to in multiplication. So there's a long way to do this, and I'm going to do one example the long way, and then after that, I'm going to show you a shortcut to calculate this product AB. But I want to do one example the long way. Let's see that. We're going to compute this product using the definition. So I need an original set of weights. And let's just call those weights X and Y. All right. Then B times those weights. Let's just write this out. B is EFGH times the original weights XY We know how to do this. The first weight goes with EG, and the second weight goes with FH. So we get X times EG plus Y times FH. And that's EX GX plus FY HY. Or EX plus FY and GX plus HY. So this is the result that we get. EX plus FY, once we calculate that out, that's just a number. And this is just a number. This is a vector that just has two numbers in it. We're going to use those as the weights for this matrix now, for matrix A. So these are our new weights. And now we get A, B, C, D times these new weights, EX plus FY, GX plus HY. All right. And the first weight gets assigned to the first column. And the second weight gets assigned to the second column. Oh, making progress. So let's work all this out. This is A times EX plus AFY. And you can't see that, so let me disappear. BEX plus BFY plus that's a C. First column is C. So those should be, I messed that up. Maybe I shouldn't have disappeared. Then you couldn't have seen me mess up. CEX plus CFY. There you go. That's a C. Plus BGH plus BGX plus BHY and DGX plus DHY. There we go. I think that's right now. When we add these together, I'm going to list both of the X terms first. So this is AEX plus BGX plus AFY plus BHY and CEX plus C plus DGX plus CFY plus DHY. Now that's a lot of writing, but this is now just a vector with two numbers. That is, all of the stuff in the top row, once you calculate it out, it's just a number over just a number. And so this is a vector, but we can separate out the X and the Y here and write this. X gets multiplied by AE plus BG and CE plus DG. And Y gets multiplied by AF plus BH and CF plus DH. And this matrix with the original weights, this is now the original weights again, gives the same answer that we have when we do B with the original weights and then A with the new weights. That combination of these two linear combinations is the same as this one linear combination. And so the matrix A times B is this matrix here. AE plus BG, AF plus BH, and the bottom row CE plus DG, and CF plus DH. All right. So that gives us an answer. So let's move on and look at the shortcut. The shortcut is called the column row rule. What we're going to do is we're going to pair up the columns of the first matrix with the rows of the second matrix. So I'm going to pair up 1, 3, and 5, 1 in this example into this pair. Then I'm going to pair up 4, -1, and 0, 2 into this pair. And then I'll combine these together. So 1, 3 times 5 is 515, and 1, 3 times 1 is 1, 3. So I multiply this column times each number in this row. And then do the same thing over here. Multiply 4, -1 times 0, and I get 0. 4, -1 times 2, and I get 8, -2. So I multiply the column by each of the numbers in the row, and then I just add these results together. 5 plus 0 is 5, 1 plus 8 is 9, 15 plus 0 is 15, 3 plus 2 is -1. So the column row rule gets us the answer much faster. We always do it in this order. So the first matrix always gets split into columns. The second matrix always gets split into rows. All right. So let's give it a try. We're going to do a couple of examples here. A and B are these two matrices here. So we're going to split A up into columns, and we're going to split B up into rows. And we're going to pair them off now. So 3, -2 pairs with 1, 5, -1, and 1, 0 pairs with 2, 3, 3. All right. So now we're going to just work out this product. 3, -2 times 1 is 3, -2. 3, -2 times 5 is 15, -10. 3, -2 times -1 is -3 and +2. Okay. Plus, and then we'll do the same thing over here. This one's very fast. 1, 0 times 2 is 2, 0. 1, 0 times 3 is 3, 0. And 1, 0 times 3 is 3, 0. We add these together, and we get 3 and 2 is 5. 15 and 3 is 18. -3 and 3 is 0. The bottom row, we're just adding a bunch of zeros, so it's got to stay at -2, -10, and +2. And this is the combined matrix AB. We did not have to work out two separate linear combinations. We just had to pair up the rows and the columns and work out the product separately. All right. Let's do one more, and then we'll move on to another topic. In this example, we have these two matrices here. We're going to split the first matrix into columns and the second matrix into rows. So that's going to give us 4, 1, 3, 0 pairs off with the row 3, 4. And 1, -2, 2, 6 pairs off with the row 1, 1. Since we need these to pair off, this is the reason for the requirement that we made at the very beginning, that the number of columns in A has to be the same as the number of rows in B. We now have a reason for that. So let's work this out. 4, 1, 3, 0 times 3, we're going to multiply by 3 first. That's going to give us 12,390. 4130 times 4 is going to give us 16,412,0. And then over here, 1226 times 1 is 1 negative 226. And 1 negative 226 times 1 again is 1 negative 226. When we add these together, we get 1317 in the top row. 3 minus 2 and 4 minus 2 is 1, 2. 9, 12 plus 2, 2 is 11, 13. And 0, 0 plus 6, 6 is 6, 6. And so this is the product AB. All right. Let's move on. We have a rule called the dimension rule. If A is an M by N matrix and B is an N by K matrix, then A times B will be an M by K matrix. Let me show you what's going on from here. That is, see if I can make this work. There, go back to here. This is a 4 by 2 matrix, and this is a 2 by 2 matrix. But this matrix right here has 4 entries because of this 4. Is the number of rows that were in this original matrix. But this piece here has 2 entries, not because of this 2, but because of this 2, is the number of columns in this matrix. And so when we combine them, we end up getting something that's 4 rows by 2 columns, but it comes from this number and this number. And so the answer to a product problem will always be the outer dimensions. The M and the K will always tell us the dimensions of the answer. All right. Big long theorem. This is theorem 12. Let's let A be some matrix, and the columns are the vectors v1, v2, and vn. These are going to be the vectors that are in A. And then X is going to be this matrix, and these are our weights. These 3 statements all mean the same thing. They're just different ways of expressing the same idea. X is a solution to AX equals B. That is, when I apply X as the weights to A, B is the result that I get. So number 2 says that B is a linear combination of the columns of A using X1 through Xn as the weights. Those 2 things mean the same thing. And then the third thing that means the same thing is that if we form a system of equations with an augmented matrix with the columns of A on the left side and this solution vector B on the right side, and we row reduce that system of equations and we find a solution that way, X will be a solution to that. So all 3 of these things mean the same thing. The transpose of a matrix, which we write as the matrix with little t, t for transpose, is the matrix that we get by writing the rows of A as if they were columns. And so as an example, if A is the matrix 1, 5, 3, negative 2, 4, 1, 3, 6, 7, then A transpose, we're just moving the data around, reformatting it so that maybe we can do a different operation with it. We're taking the data 1, 5, 3 and putting it vertically, then 2, 4, 1 goes vertically, and then 3, 6, 7 goes vertically. That's all it's there for. So in this example, if we wanted to write the matrix AT, that's easy to do. We just take the same data, we just write the rows going down. 4, 1, 1, -2, 3, 2, and 0, 6. We want to show a pattern here. So we want to show what happens when we add a matrix to its transpose and what happens when we multiply a matrix by its transpose. So A plus AT, this one, adding is easier than multiplying, so we'll do this one first. That's 1, 2, 3, 4 plus. Now we're going to transpose this matrix. 1, 2 goes down, and 3, 4 goes down. And we add these together, we get 2, 5, 5, and 8. And when we say now that it's symmetric about the main diagonal, if I look at this diagonal here, the numbers on this side and the numbers on this side are mirror images of each other. They're the same number on both sides. So that if we flipped the numbers around over this diagonal, we would have symmetry here. And that makes sense because this 5 is 2 plus 3, this 5 is 3 plus 2. And so we get a symmetry here. If we multiply A times AT, that's 1, 2, 3, 4 times 1, 3, 2, 4. And now we're going to apply the column row rule. Divide this up into columns, divide this up into rows. So we'll pair up 1, 3 column with 1, 3 the row, and 2, 4 the column with 2, 4 the row. And that gets us 1, 3 times 1 is 1, 3. 1, 3 times 3 is 3, 9. 2, 4 times 2 is 4, 8. 2, 4 times 4 is 8, 16. And so when we add them together, we get 5, 11, 11, and 25. And once again, this matrix is symmetric about the diagonal. On either side, the two numbers are the same. So this is a way of generating symmetric structures. We're going to see some applications for that much later in this course. We're just covering some preliminaries right now. All right. Let's move on. All right. I want to warn you a couple of things here. With numbers, A times B and B times A are the same. This is true for numbers. It's false for matrices. Except in a couple of special cases. If one matrix is all zeros, then you're going to get all zeros when you multiply together, no matter which order you multiply them. But normally, these are not going to be the same. So let me give you an example. Here are two matrices, but when we multiply them in the two different orders, we don't get the same answer. So AB is 2, 1, 0, 3 times 1, 0, 1, 2. Columns and rows, so we'll pair off 2, 0 with 1, 0, and 1, 3 with 1, 2. All right. So 2, 0 times 1 is 2, 0. 2, 0 times 0 is 0, 0. 1, 3 times 1 is 1, 3. 1, 3 times 2 is 2, 6. And when we add these two results together, we get 3, 2, 3, 6. But if we switch the order, now we're looking at 1, 0, 1, 2 on the left, 2, 1, 0, 3 on the right. And when we match up the rows and the columns, we get 1, 1, and 2, 1, plus 0, 2, and 0, 3. And these are different pairings than what we had before. And so obviously we're going to get a different result. 1, 1 times 2, 1 is 2, 2 in the first column and 1, 1 in the second column. 0, 2 times 0, 3 is 0, 0 in the first column and 0, 6 in the second column. When we add these together, we get 2, 1, 2, 7. And that's not the same as this. These are not equal. Right? They're not equal to each other. So matrix multiplication is not, the order does matter. It's not like a regular number multiplication, where the order, you can multiply them in either order. So on a test, be careful not to switch the order around. You might see a shortcut because it, like, one matrix looks like it might be easier, so you might want to do that one first. You can't switch the order. You have to do them in the order that they're given. Okay? All right. Here's another example. Why is these matrices not equal to each other? I don't even know what the numbers are, but if A is a 4 by 6 matrix and B is a 6 by 4 matrix, then by the dimension rule, A times B, the outer numbers of A times B will be a 4 by 4 matrix. So A times B is a 4 by 4 matrix. But if we do B times A, that's a 6 by 4 matrix times a 4 by 6 matrix. And now the outer numbers are 6 by 6. And then, so this time AB and BA aren't even the same size. And so they're definitely not equal to each other. They can't even be the same size in this case. All right. Couple of other things here. With matrices, we can't do cancellation the way that we can with numbers. With numbers, if I have 3x equal to 3y, I can just cancel the 3's and say that x equals y. I can't automatically do that with matrices. Let's see an example. B and C are not the same, but I'm going to show you what happens when we multiply AB and AC together. So AB is 2, -3, -4, 6 times 8, 4, 5, 5. When we apply column row rule, we get 2, -4 combined with 8, 4 and -3, 6 combined with 5, 5. So that's 2 -4 times 8 is 16 -32. 2 -4 times 4 is 8 -16. The -3, 6 times 5 is -15, 30. And negative 36 times 5 is negative 1530 again. When we add these together, 16 minus 15 is 1. 8 minus 15 is negative 7. Negative 32 plus 30 is negative 2. And negative 16 plus 30 is positive 14. When we do AC, excuse me, the left matrix is the same. The right matrix is different. So when we do our columns and rows, we get the same columns, but we get different rows. Ooh, all right. So let's see. 2 negative 4 times 5 is 10 negative 20. 2 negative 4 times negative 2 is negative 4 and positive 8. 2 negative 4 times 3. 2 times 3 is 6. That's not the right column. Somebody should have stopped me. Let's fix this up. I've lost my cursor here. Try this again. There we go. All right. That second column should have been negative 3, 6. Let's fix that up. Sorry about that. Now we get negative 3 times 3 is negative 9. 6 times 3 is 18. Negative 3 times 1 is negative 3. And 6 times 1 is 6. Much better. So even though these two matrices are different than these two matrices, they combine to give us the same sum. 10 plus negative 9 is 1. Negative 4 and negative 3 is negative 7. Negative 20 and 18 is negative 2, and 8 and 6 is 14. And these two results are equal almost sort of coincidentally. And so A times B does equal A times C, but if I try to cancel the A's and just say B equals C, this is an incorrect statement because B and C are different. And so we can't cancel with matrices the way we can with numbers. So matrices are more delicate than numbers. We can't change the order. We can't cancel. We can't do some of the nice things that we can do with numbers. And I want to show you one more thing that we can't do with matrices. And then we're going to wrap this up. All right. Here's another word of caution. If the product of two scalars is 0, you know one of the scalars is 0. But the product of two non-zero matrices can be a zero matrix. We don't often use the name of this law before, but you use it in calculus class all the time. Let me give you an example. If you're trying to find some critical points and you take the derivative and you set it equal to 0, and you get an equation like x squared minus 6x plus 8 is equal to 0. What do? Well, you factor this into two smaller parts, x minus 2 and x minus 4, and then you say either this piece is 0 or this piece is equal to 0. So x is equal to 2 or x is equal to 4. That doesn't work with matrices. With matrices, we can have some matrix A and some matrix B be 0, and yet we can't split this up. A doesn't equal 0, and B also doesn't equal 0. They can have zeros in them, but they can't be complete. They may not be completely zeros. So here's an example. If A is 0, 0, 3, 6, and B is 0, 2, 0, negative 1, well, you'll see what happens here. When we multiply A and B together, we get the column of A, 0, 3, times the row of B, 0, 2, and then the column of A, 0, 6, times the row of B, 0, negative 1. And that's 0, 3 times 0 is 0, 0. 0, 3 times 0, 2 is 0, 6. But then over here, 0, 6 times 0 is 0, 0. And 0, 6 times negative 1 is 0, negative 6. And now the 6 and the negative 6 cancel. And the product is 0. But A was not completely 0 and B was not completely 0 either. The zeros were spread out and distributed between them. And so we can't split those products up. And so for these three reasons, matrix algebra is going to be harder than scalar algebra, that we do not have. So these are things we do not have. We do not have AB equals BA. We do not have cancellation. AB equals AC implies B equals C. And we do not have the zero product law, which says that if AB is equal to 0, we can split them up and say A equals 0 or B equals 0. They might both have like pieces of 0 distributed among them. So, the bad news, good news. Bad news is that this class is going to be harder than a high school algebra class. But the good news is that because we can work with many values at a time in a matrix instead of one number at a time in scalar algebra, we can handle large data problems and problems involving multiple variables and the kinds of things that engineers like to work on. So we have to do harder math, but we're getting more power for that. And so that's where we're moving on with this course. All right. So I want to throw a couple of applications of these things that we don't have, so that you'll see how they work. Is this question true or false? If A and B are square matrices, then A plus B squared equals A squared plus 2AB plus B squared. This is the FOIL law, the FOIL method, where we multiply A squared, then we multiply the middle term, and then we multiply E squared. And this is false. A plus B squared is equal to A plus B times A plus B. And FOIL does work. But when we do this, first times first is A squared. Outer is A times B. Inner, though, is B times A. And last is B times B. And because AB and BA are not the same, I can't combine them into 2 times AB. And so for matrices, this business of combining the middle term no longer works. FOIL does work, but we just have to leave the answer as a squared plus ab plus ba plus b squared. We can't simplify it further. So this is a false statement. All right. The difference of two squares. So a squared minus b squared, we can factor that into a plus b, a minus b. Well, that also has a problem. If we FOIL this back out, we get a times a is a squared. Outer is minus a times b, but inner is plus b times a. And last is b times negative b, that's minus b squared. The right side is equal to this, and these might not cancel. For numbers, we can say negative AB and BA is the same as negative AB and positive AB, and so they cancel. But for matrices, they might not. And so this statement is also false. All right. One last definition and a couple of examples we're going to wrap up in a moment. We say that a system of equations is homogeneous if b is equal to 0. The constant terms are equal to 0. So all homogeneous solutions have at least one 0. Because if I take A and multiply this by the weights 0, and I don't know how many weights there are going to be, then the answer will always be 0, because I'll take 0 times the first column and 0 times the second column and 0 times the third column. And so I can always solve a homogeneous system by just taking 0 times all of the weights. That works. We call it the trivial solution. From an engineering point of view, it's not very useful if you shut everything down and don't produce anything, and you don't have any times anything, you get nothing, but you're not actually doing anything worth that. So the thing that we're interested in is if the homogeneous system has a non-trivial solution. And in order for it to have a non-trivial solution, that means we have to have more than one solution. And that means the system has to contain a free variable. So let's look at an example. We're going to show that the 0 vector is the only solution to this homogeneous system. So if I look at the augmented matrix here, and we can put it into echelon form very quickly. It only takes one step to put this into echelon form. I have to just get rid of this 2. So I'm going to take row 2 minus 2 times row 1. So then 2 minus 2 is 0. 3 minus a negative 4 is 7. And 0 minus 0 is 0. This is an echelon form. But x is not free and y is not free. Because we have a leading entry in the x column, and y is not free, and because we have a leading entry in the y column. And since neither of these variables is free, then there's only one solution. There's no freedom in this system, so we only have the one solution, and it must be the trivial solution. X equals 0 and y equals 0. And so the 0 vector is going to be the only solution to this system. All right. All right. Well, thanks for coming. We are going to start a new section in the next video, and I look forward to seeing you then. Take care.